Hello everyone, I am Anubhav Patel and today I will be presenting on steady state radial heat conduction in hollow cylinders without heat generation. This topic is very important in transport phenomena because many real life systems like pipelines, heat exchangers, boilers and reactors involve cylindrical geometries. In this presentation, I will first explain the basic concept and then derive the governing equations for steady state one-dimensional radial heat conduction, and finally discuss important applications such as log mean area, electrical analogy, critical thickness of insulation, and overall heat transfer coefficient with numerical examples. Let's begin with the basic idea of heat conduction. Heat conduction is the transfer of energy due to temperature difference within a material without any bulk motion of the material. As I have already said, this topic is very important in engineering context because it is essential to analyze systems with cylindrical geometries because the systems might be having a cylindrical geometry such as pipelines, heat exchangers, nuclear reactors. Let us discuss why will not the plane wall analysis will apply to this. In simple plane wall, heat flows through a constant cross-sectional area, so temperature decreases linearly from one side to other. However, in cylindrical systems like pipe, the situation is different. Here the area through which heat flows is not constant. It depends on the radius, and as we move outward from the inner surface to the outer surface, as we move from outward from the inner surface to the outer surface, the area increases. This means heat spreads over large area as we move outward, which changes how temperature varies. Because of this, temperature profile becomes logarithmic instead of linear. To simplify the analysis, we have made some assumptions. First one is there are steady state conditions, meaning the temperature does not change with time. Other one is there is no heat generation. Third one is third one is heat transfer is only in the radial direction. The other one is material properties are either constant or vary in a known way. These assumptions allow us to reduce the problem to a manageable mathematical form. And moving on. Now we will consider a thin cylindrical shell of thickness delta R, and we will apply an energy balance on this element. At steady state, the heat entering the shell must be equal to the heat leaving it. So we write heat in minus heat out equal to 0. Mathematically, this will be written as like this. Taking the limit as delta R tending to 0, we will have this expression after we divide the both sides by delta R. Applying the definition of derivative, we arrive at this expression dAQR by dr equal to 0. The radial heat transfer QR is constant across any radius. So even though heat flux changes, the total heat flow remains constant across all radii. Now we will use Fourier's law, according to which heat flux is proportional to the temperature gradient. Substituting substituting the Fourier's law into the equation, and integrating, we obtain the temperature distribution. First, we will get the integration equation something like this. And the boundary conditions given to us is at T at R equal to R1, we have the temperature equal to T1. At R equal to R2, we have temperature equal to T2. Integrating the previous equation and applying the boundary condition, we arrive at the heat transfer rate as this, and we get the temperature distribution as this. The final expression shows that temperature varies logarithmically with radius. This happens because area is continuously increasing, so the rate of temperature change adjusts accordingly. And as a special case, when we assume k to be constant instead of function of t, then the above heat transfer rate can be simplified as this form. And similarly here, k will come out of the integral from both numerator and denominator, and the expression will be simplified as given as this. As from the derivation, we have got the expression for the heat transfer rate. Clearly, it involves the ratio of outer radius to inner radius. This clearly shows that geometry plays a direct role in determining heat transfer. To simplify analysis, we use an electrical analogy. Here, temperature difference acts like voltage, heat flows like current, thermal resistance act like electrical resistance. So this mathematical equation can be translated to the given circuit where resistance equal to ln R2 by R1 divided by 2 pi Lk, which can be obtained from this equation here, where it can be mirrored as rate equal to driving force divided by resistance. Now, here comes an important concept, log mean area. In cylindrical systems, area is not constant, so we cannot directly use planar formulas. Instead, we define an equivalent average area called log mean area. It accounts for the exponential change in area with radius. Using this, we can write resistance in a form similar to planar conduction. So, log mean area bridges cylindrical and planar heat transfer. It can be defined as this: ALM equal to A2 minus A1 divided by ln A2 by A1. Putting the value of log mean area into resistance, we arrive at the expression resistance equal to R2 by R2 minus R1 divided by K log mean area. As I have already told, the log mean area allows cylindrical conduction to be expressed in a form analogous to planar conduction. Now we are going to see heat transfer using bulk fluid temperatures. Why bulk temperatures? Because surface temperatures T1, T2 are usually known. Now we will see the heat transfer using bulk fluid temperatures. Why bulk temperatures? Because surface temperatures T1, T2 are usually unknown and often difficult to measure. So therefore we will use bulk fluid temperatures. We have TA for hot fluid and cold fluid for we have TV. Then we will apply Newton's law of cooling to both the surfaces, and we relate surface and bulk temperatures using convection equations. Rearranging the above equations, we arrive at these equations from earlier equations. We have conduction through cylindrical wall equation like this, and adding all the three equations, we arrive at the overall temperature difference, which is the sum of inner convection, wall conduction, and outer convection. The previous heat transfer rate equation can be expressed as an electrical circuit where TA minus TV can be expressed as the driving force, and that whole term in the numerator, in the denominator, sorry, not denominator, in the denominator can be expressed as the total resistance. Hence, our derived heat transfer rate equation can be transformed to electrical circuit according to Ohm's law. Now we will look at overall heat transfer coefficient in cylindrical system. We have the general expression as this: UN, UA and UV are the overall heat transfer coefficients which are based on inner and outer surface areas. Based on inner surface areas, we have UA, and based on outer surface, we have UV. UA and UV both represent same physical heat transfer. but, but they refer to the different area. Now moving on to numericals, we have a numerical where we have been given inner radius and outer radius, the temperature of inner and outer surfaces, and thermal conductivity, which varies with temperature. So we cannot assume it constant. And our objective is to calculate the steady rate of heat transfer. The approach we would follow here is simple. Since the thermal conductivity varies with temperature, we will not assume it to be constant. Instead, we will express K as a function of temperature and integrate. This gives a more accurate heat transfer. Finding the expression for the K and substituting values in the integrating equation, we arrive at the final calculation here, and we get our answer as 42,382 watt, and hence our this numerical is done. Now moving on to the next numerical, we have been in the second numerical, we have been given a cylindrical pipe with inner radius R1 and outer radius R2 and insulation added up to radius R3. Now we have to study and show how heat loss varies with insulation thickness. Our key concept is adding insulation does not always reduce heat loss. It can initially increase heat loss. The reason is because the increase in surface area is compensated by thermal resistance. We usually think that adding insulation always reduces heat loss, but in cylindrical systems, this is not always true. When insulation is added, resistance increases, but surface area also increases. Initially, the increase in area dominates, so heat loss increases. Then, at certain radius called critical radius, heat loss becomes maximum, and this is called the critical radius. We will move it to. We will first write the overall heat transfer expression and assume the whole term in the denominator to be s. And instead of assuming whole denominator terms to be x, we will go and assume these two terms to be x and differentiate x with respect to R3 so that we can get their what we call it critically critical condition. Differentiating x with respect to R3 and equating the whole expression to 0, we have R critical equal to Ki by Hv. At R3 equal to RCR, heat loss is maximum. Hence, our key observations from this question is that when R3 insulation thickness is greater than R2 but still less than R's critical radius, heat loss will increase. But after critical radius, heat loss will decrease. And we can find the graph here. Now in this example, we analyze three cases based on dominant resistance. We have the equations for overall heat transfer coefficient given as this. And our key idea is to compare resistances to find the dominant region. For the first case, we have H equal to 10, H equal to 5000, K equal to 2000. And the dominant region in this case is the fluid A. And using that equation, we will approximate the value of the overall heat transfer coefficient, and the temperature profile can be sketched like this. We can see clearly fluid A dominates, and similarly moving on to the next cases. For the second case, in second case, wall conductivity is low, hence wall dominates, and there is a large difference across the wall, and the temperature profile sketch is given. Similarly, in the third case, outer convection is weak. Fluid V dominates. Fluid V dominates, and there is a large drop in fluid V. sum it up, the largest resistance always causes the largest temperature drop. We are done with this numerical also. Now moving on. We have successfully done the study analysis. Thanks for watching.